What's up, guys? What we're looking at here is my hydrogen torch that froze up on me this winter. I neglected it. I usually put a little 20-watt light bulb inside the cage area there, and that keeps it heated enough through the winter that it doesn't freeze up. But this year I just got so busy I forgot to do it, and it needs some serious servicing. Also, this is still in its development stages. I know I've been working at this for like 10 years, but this design right here has basically taught me all I need to know to build my final device. This is not the final construction. This is still just the testing phase. This thing works great. One problem was it froze up on me and has busted a leak. One of these fittings was pushed out by the ice. I would imagine that a large ice slug formed in that radiator and grew like half an inch and push those out. I'm thinking my electrolyzer probably didn't expand. Might not have been enough ice in there to do that, but who knows. So I'm halfway tempted to just tear the whole thing down and do an overhaul on it, because this thing's pretty old and it's full of water and sodium hydroxide solution. So it's got a pretty caustic environment. And I notice I've got a couple of little leaks down inside of here. Let me get the light going. But I just want to do some things to this to make it better. Yeah, you see that terminal right there? There's a leak right there. You know, and any little leaks that get up in this thing can cause this thing to ground itself out in strange ways where it doesn't perform quite as well. I think it's just ready for a complete tear down. Like I said, there's some things I want to do to it as well. I don't like where that pump's at. I don't like the fact that I only have one top foam jet. I'd like to have 4 of these at the top to knock the foam down when this thing's running at like 20 amps, because at 20 amps the water gets very foamy and bubbly from all the micro bubbles and stuff. But at any rate, I just thought it'd be kind of cool to take this electrolyzer open for any of you HHO guys and see what an electrolyzer made out of high-grade stainless steel looks like after many years of service. And I have tortured the cell. I've had this thing up to 20, 22 amps. A cell that size. That's AC input, so what are we looking at there? Like 2,400 watts or something like that? I don't have a calculator and I'm too stupid to do it in my brain. 125 is my voltage out here times 20 amps. Yeah, 2,500 watts of power has cranked through this thing. That comes out to about 5 to 5.5 liters per minute. It's not the most efficient cell. Another reason why I want to take it apart is because I want to go with a 2mm plate gap. I did some reading and found some Department of Energy documents that showed some graphs that indicated the optimum plate gap is 2 millimeters. So if I buy some 1/8 inch gaskets, they would compress down to about a 2 millimeter plate gap. And this radiator, anytime you see someone who builds one of these torches and is trying to sell you a torch or something, or is promoting their new torch they built and it doesn't have a radiator on it, I want to tell you something. Don't buy an HHO torch from anyone that doesn't have a radiator on it. These things crank out way too much heat at anything over 10 amps to be usable for anything that takes a while to do. If you're just doing some short bursts, but they have like a 10% duty cycle without a radiator. I'm serious, like if that, maybe only a 5%. So, I don't know. I just don't like this radiator either. It's too small. It can actually heat the fluid up if you have it racing through there real fast. This pump does have a variable speed knob on it, so I can adjust the speed, because like I said, if you're actually trying to cool the fluid and you have the pump turned on high, you can actually add a lot of heat to the system from the pump alone. And with a radiator this small, that also is a problem. That you actually heat the fluid up 10 degrees just by circulating it on high. You can still remove a vast amount of heat from it with a fan being blown on it, but that's pretty much how it behaves. I do have a thermocouple that's hooked up to this thing. That's basically just a, you see that T fitting right there? I stuck the thermocouple end inside of a piece of tubing and it fit right in there perfectly, and that's glued in with goop glue. All of these joints are done with goop glue. So if you're wondering whether or not goop glue can handle caustic solutions, this stuff performs fantastic. These joints are about 5 years old and they feel brand new. Still got some play to it. I'm starting to itch. I must have that stuff on me somewhere. That sodium hydroxide will burn you. So yeah, the thing leaked quite a bit. I just think it's going to be cool to tear this down. I'd hate to do it because it's a lot of work, but I figured I might as well document some of it because it's kind of cool. So unfortunately, I'm going to have to hold off on the projects I have going right now with the waste oil burners and all that, because it's just the weather is just not permitting and I can't do any valuable experiments in this garage. So we're going to tear this bad boy down. I'm tired of not having it. It's so valuable to build stuff with. Such a fine laser-like flame that I've learned to fabricate things with it so easily that I just don't like using propane torches anymore for soldering and stuff like that. At any rate, there you have it. We're going to tear this sucker apart, see what the inside of that electrolyzer looks like. I'll get the actual date that I first threw this bad boy together. I want to say it's 5 years old. I could be wrong. It might be a 2014 build. I left the fins long, or the plates long, to double as cooling fins on the electrolyzer. I thought that was kind of a pretty cool design feature. However, stainless steel is a horrible conductor of heat. It still was a pretty decent idea. That there is just a copper bus that was silver soldered along the whole plate there. And that there is a jumper that jumps current over to the other side of the cell. And the reason it does that is because stainless steel is such a horrible conductor of electricity that had I simply connected the terminal on this one side, the resistance from this side of the cell over to here is equivalent to 200 watts. That's like having the heat dissipation of a 200 watt light bulb in your hand. Could you imagine that? So yeah, never use stainless steel to transfer electricity. Luckily, the plates, when they're stacked, are thin enough. In theory, if one were to make like paper thin plates or super thin plates, you would probably get some outstanding performance increases due to that, because I'm not lying about that 200 watts thing. Maybe not quite 200 watts, but I bet you it's every bit of 150 for a distance that small. I seen a guy did the calculations on some cables about the length of my hand, and it was 200 watts of electricity was, or 200 watts of energy being dissipated, 200 watts of energy loss, or something, some insane amount. And stainless steel does act like nickel wire. For example, this piece of wire right here is 1,000 watts of electricity. That's nickel wire, and they use that because it's a I'm pretty sure it's like a stainless steel alloy with nickel and chrome in it. I could be wrong. That's why it's called nickel, maybe. At any rate, the same thing is done to the other side of the cell. I have that jumper wire that carries electricity to the other side of the cell, and the end plates on this are just steel plates. They are not electrically charged in any way. They are basically slapped right up against the back of this first plate right here. That whole thing's silver soldered together. It's about $22 worth of silver solder on this thing for the terminals. Also, if you have a hydrogen torch and you use it a lot, remember periodically to reverse the polarity on your electrode, because the negative side, the hydrogen producing side, or the cathode, will blast off rust and accumulation that results from being an anode for so long. If you'll notice, in most hydrogen cells, the hydrogen side is always perfectly clean. However, it's the oxygen side that degrades and builds up stuff. And At any rate, let's get on with this. Man, I've got quite the job. It's amazing how much wiring is in just a simple little machine like this. There's really not much to this thing, and yet every terminal is used up on this block. We have 2 cooling fans and 1 coolant pump or circulation pump. The electrolyte is circulated by a bubble displacement pump. Basically, as the bubbles rise up this pump, tubing, they cause the water to flow, and it will pump water out those nozzles and pull water down from the bottom, and it causes a self-induced circulation by the appropriate allocation of bubbles, basically. I've had cells in the past where I would have a pump that would actually force liquid into the cell, and that does seem to increase performance, and I may be doing that again with this cell, because the benefits of doing that are that you have far more electrons can pass through the electrolyte that way. If you have 1,000 million bubbles all in one spot, not as much electricity can pass from one plate to the next. When your cell is saturated with bubbles, its resistance is higher. But if you flush them bubbles out as fast as you can with the fresh replenishment of electrolyte, it definitely increases the output of the cell. And you can watch it happen. You can turn your cell on and it'll be running at, say, 10 amps, and then you kick a circulation pump on your cell, and all of a sudden that cell will start to draw up to 15 amps just because you're forcing electrolyte into the cell and you are depolarizing the plates. That's another aspect. When bubbles accumulate on the plates of any type of electro cell, being a car battery or anything, that is called polarization. Have you ever experienced trying to start a car that won't start, and all of a sudden the battery's dead, but then you wait a while and you come back and you try starting it again, and for some reason the battery appears to have recharged itself? Well, no such thing has happened. Actually, what has taken place is that when you cause a massive discharge in a cell, or a massive input of electricity in an electrolyzer, bubbles accumulate on the plates of that cell, which diminishes the active surface area of the electrolyzer or the battery. So if you're cranking your car and your battery's electrodes become saturated with micro bubbles on the plates, now your battery's down to only 220 amps versus 380 where you need to be. So you let it sit for a little while, and those bubbles will actually either dissolve into the electrolyte or will float up to the top after they have coalesced. Or what's the word I'm trying to say? I can't talk right now. I don't think coalesce was the word, but at any rate, when they glob together. So having the pump force electrolyte through there diminishes the polarization of your plates, and I don't have that feature right now. I'm just using the gravity pump system, and I'm starting to wonder if that was a good idea. Maybe I should switch it back. But consolidate, damn it, that was the word. The bubbles consolidate into larger bubbles until they finally float up in your battery, and then after those plates have consolidated and have either dissolved back into the electrolyte or floated away, your battery will have more active surface area contacting the electrolyte, increasing the amperage of the battery, because the amperage of a battery or an electrolytic cell is directly proportional to the active surface area. So the more surface area you have, the more plates you have in a bath of battery acid, the more amps you're going to get. When those plates get bubbles on them, all right, I'm beating this dog to death here. We got to drain the toxic, nasty stuff that's inside of this thing and put it in a container and draw a skull and crossbones on it, basically. Because the stuff's pretty nasty. These stainless steel cells have a byproduct called hexavalent chromium, which is carcinogenic. All right, it must be time to eat because I have suddenly lost the ability to talk. But I just want to get one last look at this thing because we're never gonna see it like this again. I kind of get attached to my builds sometimes. This is definitely one of the coolest things I've ever built in my life. It's just an awesome tool, and I have built a lot of things with this, and I think it's time that I take it apart one more time. And if you guys have any comments or any input regarding some hydrogen torches you have built in the past, definitely hit me up with some info, because this is gonna be the grand finale, this last build. I'm gonna make this happen. I hope I don't spend a whole bunch of money on this thing. I mean, to give you an idea, if you were to go out and build this, guys, you're looking at $1,000 right here. That is no lie. Every bit of $1,000 is right here. And I got this stainless steel for free. And cut the plates and got the gaskets for free. And you're still looking at $1,000. I mean, I don't know how, but I spent a lot of money on this thing. The pump, you know, all the hose, all these fittings. These fittings are like $5 a piece. So, all this electrical stuff, the diodes. I've got, I believe this is 3 diodes on this thing that are hooked up in parallel. So here we are, getting down into the nitty-gritty here. Man, I had some stuff going on here. Look at that metal debris I've got right there. That might just be paint, but I'm inclined to believe that's metal debris from me drilling my water pump in place. Surprised that didn't get blown out of there when I blew this off. Stuff like that can cause problems. It looks like my plates are just squished beyond belief here. I'm at a very thin plate gap right now. I'll do some measurements on this before I shut it down, but or before I take it apart, I mean, to see what plate gap we're actually writing at right now. There's a plate in between every one of these plates that you can't see. It's sandwiched in, the gaskets have just sandwiched over it. This thing's just been compressed so badly. There is a plate in between there. It's the same thickness as that plate. So we're in an extremely low plate. Matter of fact, I think I have a spare right here. This is the high grade stainless steel that I used to build this cell. This is came out of an air duct system in a hospital. It was a scrap. Oh yeah, we're at a pretty thin plate gap right there. Actually, we might be at about 2 millimeters. Hard to say. It's gonna change when you get closer down in there though. I think I just touched some sodium hydroxide. It's actually sitting at a pretty decent gap. I doubt I'm gonna be able to reuse these gaskets though. So that's gonna be a deal, but very interested to see what condition these plates are in. This plate is, I don't know what grade stainless steel this is, but it did zero magnetic. A magnet will not stick on it whatsoever. None of that 304 crap. I want to say it's 316 stainless. I would imagine it is. It was in a hospital air duct system. And I'm sure they had that baby rated for 50 years. Man, look at the thickness of that. There was entire air ducts of this. Really high grade stuff. And I managed to get my hands on a dab of it to build that cell. So I'm gonna shut up and keep tearing this thing down. Let's see what's inside this sucker. So here's the electrolyzer taken out of the machine. As I said, in between each one of those gaps is a short plate. The long plate is just for a cooling fin effect. I have 2 intakes, one on the bottom of each side, and 2 discharges on the top. That is to allow for maximum flow, because you got a lot of bubbles coming out of the top. You need to make up for that volume, and the volume of the bubbles is significantly larger than the fluid flow going in the bottom sometimes. So definitely an added advantage to waste the extra money on that hardware. These parts are like $5 a piece. These elbows, I believe, like $5.30 or something. And as you can see, I've got quite the pile. These valves are like $5 a piece, I'm pretty sure. I can't remember what these parts are worth, but they don't cost as much. But just a quick walkthrough, if you're interested, at the components of this torch. This is the control panel, which would be completely revamped. As I said, this whole thing was just a test unit. This is the cooling fan for my triac, which has come loose. Both of them are kind of loose. This one I'm not too worried about. I probably should have never put it on there. It's only for the cooling fan anyway, or for the circulation pump, which it doesn't cause enough heat really to dictate putting it on here, but I did it anyway. On my next build, I might connect 2 triacs in tandem to make it a little bit more robust. And here's all the other stuff we got going on. This switch controls the fans, so I don't have to run the fans continuously, because you don't want these things running when you don't need them on. It just gets dust all inside your cooling fins. Makes for a job. This here is the thermocouple. You definitely want to have a thermocouple on your torch. You don't want to be running your electrolyte at boiling temperatures or anywhere near 150 degrees or anything like that. I don't think it's a good idea to do that anyway, because the gaskets tend to start getting soft, and you risk getting leaks because the tubing gets soft as well. This here is the diode array. It's made out of 3 diodes to be exact. I want to say these are 50 amp diodes. Could be wrong. There might only be 15. I'd have to check into that. I know that I have way more than I would ever need. And what happens is 125 volts AC goes into these diodes and comes out about 120 volts DC on this end. And that's what we put into the electrolyzer. And the way these cell electrolyzers work is there's no electrical connection between here and here. The electrolyte does that, and the plates do that. And because each cell is divided by a plate, something very strange happens. A transformer effect takes place. And where in between each plate on this cell, I believe I'm at around 3 volts per plate gap, maybe a little more. I like to run it high because you get far more output. It's not efficient, but you get more output out of a cell. I've run as high as 4 volts per plate gap, but that starts to really eat it up. I'm right around 2.2 volts to 3 volts on high. I would have to check my records. I don't have my booklet out here, but that's the amazing thing about using a dry cell, is that you don't need a transformer. It does it for you. If you check the voltage in between any one of these terminals, it comes out to like 2.3 volts, which is pretty awesome. But here's the cool part. I'm only putting 20 amps AC into this, but we're getting the 120, we're getting the 20 amps DC cranked into it, and what happens is that 20 amps DC is jumped down to 2.3 volts at the first plate, because it's 2.3 volts in between each plate. So you know what that means, don't you? That means we have to have like 1,000 amps of current pass between this plate and the next one to enable 2,400 watts of power to pass from this plate to the next. The amperage has to go way up, and that's exactly what happens. And that's why these cells are so tremendously effective at producing oxyhydrogen gas. They're amazing electrolyzers. They're the best, and that's why they're the best, because the amperage is built into the system. I mean, the transformers is built into this electrolyzer, and it's a highly efficient mode of converting your voltage to high amperage. I know that sounds crazy to people who aren't familiar with electricity, but you can actually pass 1,000 amps from one plate to the next if your voltage is only 2.3 volts. I mean, go look at some microwave transformer videos and you'll see what I'm talking about. But that's the beauty of this particular design, is it will do that for you. So now what we're going to do though is just kind of inspect it. It doesn't look like, oh crap, I should have drained it a little better. That's going to start eating a hole in my aluminum. Not cool. Give me 1 second here. Okay, we can see a couple of spots that started to fail on me. I didn't have this glued up very well. I could have done a much better job. These ones did fantastic. You can see where that started to cause some problems. Current will start to flow in strange paths when you have conductive leaks. I tell you what. So that's going to get taken out and burnished and resealed and all that good stuff using goop glue. You can see I have these all threads are electrically isolated from the plates in case a plate were to sag down. You can almost see the old plate stacked this way. Kind of see it. Yep, some of those are just smushed in there and you can't see them. But we've got a little bit of a leak on the side down here too, it looks like. And what will happen is if you have a leak in the front of the cell, right, and fluid gets down into a puddle, and then you have a leak on the other side of the cell, and you have a fluid that connects these two areas, you'll get a leak. An electrical charge leak will be going from here, it'll travel through this leak, through this slush, down onto the floor of the electrolyzer, up over here, and will jump through the cell and cause sparks and hissing and sizzling sounds and all kinds of weird stuff. So it's going to be interesting to take this bad boy apart. It had a good run. It lasted a long time. Can't ask for too much more for something that I built. But yeah, let's get this thing apart and see what kind of shape these plates are in. This here is the pump. I'm very impressed with this brand of pump. I think I've had this pump running an electrolysis cell for well over 5 years because it's been in other builds running other electrolysis cells. Definitely endorse this brand here. These guys make a really good pump. This is a 3-speed pump on the box. I also run it off this triac here because sometimes, as I said, you don't want to run your cooling circulation fluid too fast because doing that will actually add 10 degrees to the fluid in this particular system. This here is a foam catch. Sometimes when you're running your cell at 20 amps, the electrolyte starts to foam up really bad and will shoot out the top of the cell into the discharge line. And you don't want that stuff getting into your bubbler. So this is placed in series with the discharge line on the top of the reservoir. And what will happen is the foam will come into this tube, and by the time it passes through the hose that gets to this tube, it's converted back into fluid, and eventually this will get full of electrolyte as you're brazing away or whatever it is that you're doing. If you've got a big brazing job going or something, it will fill this up maybe to about right here or so. And then what happens when you turn the torch off for the night or after the job, the large airspace inside of this thing will cool off and will contract and will actually draw this fluid right back into the tank, and you'll end up with just the same amount of electrolytes you had before, which is a pretty cool little setup. This here is the radiator that has had a leak for a while. The goop was holding out pretty good though. Had a leak there, and it had a pinch in the line somewhere that was causing some heating from just flow issues. You've got a bunch of eddy currents and stuff in your flow system. That will heat the fluid up. This is the bubbler, as they call it, which basically creates a physical barrier between the torch flame and this massive bomb right here called the reservoir. So if the flame were to ever travel up into the tube, it would just come down inside of this bubbler and explode inside of here, but it won't go down through the bubbling water. It doesn't daisy chain through the bubbles for whatever reason. It just, I think part of the reason is when it first explodes, the bubbles are compressed and contract so small that they're not close enough to each other to self-detonate. That's just a theory, but I guarantee a high-speed footage of that incident taking place would show that to be the case. Because I've always wondered why the bubbles don't just explode and travel right down into the reservoir, but they never do. This here is my reservoir. Been running this thing for probably over 5 years also. It's the only plastic so far that I've seen that doesn't suffer the fate of stress corrosion cracking or hydrogen embrittlement. This here is sealed off with just goop glue. That thing's holding out real nice. Definitely happy with how goop does in these caustic soda solutions. But at any rate, I just wanted to show you guys the components that went into making this thing and why it would cost so much money. This stuff just isn't cheap. When you go to build a machine, plan on spending some serious jack, because these parts are not cheap. I mean, look at all these fittings I have. There's freaking hundreds of them. And they're, like I said, these ones here are $5 a piece. And it just starts adding up pretty quick, real quick. This reservoir itself, I think, was probably $40. You got a $3 brass plug here. You got a $3 elbow, $3 quarter-inch MIP. It just adds up and adds up. This thing here was like 30 bucks. This is supposed to be a filter, but I converted it into a bubbler. This here, $12. This pump is 100 bucks. The diodes were probably 15 bucks a piece. That little fan was free, but I'm pretty sure that these junction boards or junction blocks are pretty expensive. I think they're like $15. That transformer was probably 15 bucks. $15 there, $30, $30. Probably about 10 bucks. Got $9 on that hose right there. $3 switch. Another cooling fan and block. So yeah, man, the wire, these terminals, it just adds up and adds up. The all thread for all this, these copper bus bars, I silver soldered those on there for maximum conductivity. I didn't want to just use regular solder because yeah, that's just how I roll, I guess. So I'm going to shut up now and start tearing this thing apart. One of the tricky things about this build was that these two bolts that compress the filter press design together had to be electrically isolated from these plates. I couldn't have these two plates being connected electrically, so I had to use plastic nylon washers, and I had to tape the all thread. But just the slightest leak of fluid getting on there can cause problems with that. This thing has expanded out pretty much. I'm going to have it apart here in a minute. This ought to be pretty interesting to see what this thing looks like after years and years of use. You guys are not going to believe this. If you're an HHOer and you build hydrogen torches, you'll appreciate this one. What you may be seeing here is the result of a practice that I always engage in, and that is I will constantly reverse the polarity on my electrolyzer. I talked about that in the video already, but you probably might have skipped over it. I would imagine I'm quite boring entertainment when it comes to me yapping. But dude, look at these plates, man. They're in pristine condition. I don't have to do anything to them. I might be able to just reassemble this bad boy as is. I mean, of course, I'll have to fiddle with these gaskets a little bit. I didn't use any compound. It took quite a bit of had quite a struggle getting these things to set right and getting it leak proofed. I had to keep tightening that thing down. That stack started off, say, this tall. By the time I got done, it had smashed down that far, man. I swear I got 3 feet out of that sucker. I'm going to take a look at these end plates real quick. This was this part I was really interested to see how this is going to go. I was concerned about this. Ah, that sucker ain't coming off of there. Very nice that these plates withstood that so well. Okay, I'm having like serious problems here. I gotta set the camera down to pull this off. However, I am just shocked. I cannot believe how clean these plates are. I was expecting some rust. This truly was some high-grade stainless steel, I can tell you that. I've built plenty of cells in the past that didn't do so well. I probably have a stack of plates I could show you real quick, actually, just for the sake of comparison. I've got a whole stack right here. I should add some plates to that cell. I don't know why I don't do that. I think I might. These are some other old plates that I have. You can see these guys didn't fare so well, and this is not after very long use. Look at that compared to this thing. Pristine shape still. I'm almost afraid to. Now, as I said, I did constantly reverse my polarity. I swear these things feel like they're shocking me. Little bit of smudge there, some material. I could probably use a slight cleaning, but not much. So you definitely want to, this is an interesting little area right here. It looks like we had a gasket about ready to blow out, maybe. Look at that. See how that's got kind of a, that might have been squished out too from high pressure. You can see my gasket path wasn't very wide right there. This is the piece I want to get torn off. Had a little bit of a leak there. I see part of the problem why I'm not getting this off. I'm sitting here pulling on that like an idiot. So yeah, I got to get that wire off of there, dumbass. That's a jumper. Damn near get that off. I had these out of here. Oh, man, them babies are in there. That's what I like about goop glue, is it's reversible. Man, I could just sell that stuff all day. Definitely a huge fan of goop glue when it comes to fabrication. There's just some stuff that you can't get to quit leaking. This is the part I really wanted to see, was what this looked like here. This interface right here. This is steel. It didn't leak too bad at all. I was worried about these things getting electrolyzed and this iron eating away real bad, but it's in really good shape. I'm really happy with that. Really happy with that. It looks like there might have been a little bit of activity taking place, some seepage. You can see the holes. Other than that, yeah. So I'm definitely pretty impressed with what we're seeing here. Very glad that this thing isn't all rusted to death. It's got a little rust on her, but nowhere near what I was expecting. I can't believe that. This is my terminal plate, and it looks like my solder joint might have cracked off there. I have really heat stressed the heck out of this thing. Yeah, something was going on with my solder joint there. Top side still looks good. Huh. I'm gonna have to redo those solder joints. Those are unacceptable, in my opinion. What the hell was I doing? Did I just not see that? Who put this damn electrolyzer together? You're fired. Yeah, I dropped the ball on that, guys. That's just not a, that's a piss poor job for sure. Look here at the front. What the hell was he doing? Well, there's not that much amps going through it, but still, it defeats the purpose of putting a bus bar on there if you're gonna solder the thing like that. I mean, I doubt that melted on me or something. So there we are. I am just very impressed. I do want to check the thickness of these gaskets real quick to see if they're 2 millimeter. Or not 2 millimeter, 1/8 inch. There's no way those are 1/8 inch gaskets. I want to buy some gaskets that are thicker than this. These are like just off of a roof somewhere. Yeah, 0.076. I think 1/8 inch is 3 millimeters, isn't it? So let's just do millimeters. Okay, so no way. These are not 3 millimeters. Plus, when you compress them, I mean, I don't know if I'm going to be reusing these gaskets. I really don't. But I'm going to clean this mess up. Clean these plates up a little bit. I am impressed with how good of a shape these plates are in. That is amazing to me. You can see the one side is a little dirtier than the other. The hydrogen side versus the anode, the oxygen side. Now, had I did that little reversal right before I took this apart, we wouldn't see any of that. It would have blasted all that off there, because it takes anode accumulation a very long time. But it blasts off there like in days. So I think I'm going to call that a wrap on this one here, guys. I just thought you'd be interested to see what the inside of this cell looks like. And I'm telling you right now, this thing has had some serious miles on it. I'm starting to eat a hole in my aluminum block here. I got to get this crap off here, but tell me what you guys think. That's some good stainless steel right there.